Assalamualaikum warahmatullahi wabarakatuh. We are from group 1 and we want to talk about decomposition of hydrogen peroxide. Hydrogen peroxide is a pale blue liquid that is widely used as a disinfectant, bleaching agent and oxidizing agent in household, laboratory and industrial application. Even though it seems stable during storage, it is actually thermodynamically unstable and gradually break down into water and oxygen. Understanding this process is important because it affects both how long hydrogen peroxide remain useful and how safely concentrated solution can be handled. This breakdown of hydrogen peroxide is known as a disproportionation reaction, where the same substance undergoes oxidation and reduction at the same time. The overall balance equation for the reaction is 2 mol of hydrogen peroxide equal to 2 mol of H2O plus O2. The reaction releases a large amount of heat, making it an exothermic process. This high energy output explains why concentrated hydrogen peroxide is useful in certain propulsion applications. However, the reaction proceeds slowly at room temperature due to a high activation energy. When a catalyst is introduced, the activation energy is reduced, allowing the reaction to occur much faster.
Today, I want to show you the decomposition of hydrogen peroxide. As we know, hydrogen peroxide can be used in many experiments, but I choose to show you guys elephant toothpaste experiment. Let's watch this video together. Elephant toothpaste experiment is a reaction where hydrogen peroxide rapidly decomposes into water and oxygen gas. The oxygen gas gets trapped in soap, producing a large amount of foam, like we see in this video. So, in this video, we will use hydrogen peroxide, liquid dish soap for trap oxygen as bubble, food coloring for visual effect, and yeast as catalyst. What happened in the reaction? Hydrogen peroxide breaks down naturally but very slowly. The catalyst speeds up the reaction without being used up. To sum up, the elephant toothpaste experiment demonstrates the rapid catalytic decomposition of hydrogen peroxide into water and oxygen gas. The presence of a catalyst significantly increases the reaction rate, producing a large volume of foam and releasing heat. This experiment clearly illustrates the role of catalyst, exothermic reaction, and gas formation in chemical reaction.
Now have a look at reaction kinetics and catalysis. Catalysts also play a major role in this reaction. They speed up the decomposition by lowering the activation energy. Without a catalyst, hydrogen peroxide decomposes slowly, but with catalysts such as iodide ions or the enzyme catalyst, the reaction becomes much faster. Next, we move to iodide catalyzed mechanism. In the iodide catalyzed mechanism, the reaction occurs in 2 steps. The first step is slow and forms an intermediate called hypoiodide. The second step is fast, producing water and oxygen. Since iodide is regenerated at the end, it functions as a true catalyst. For the rate law, rate equal to K bracket hydrogen peroxide and bracket iodide. We can determine the order from the experimental value given. So, as we look at here, the order for the hydrogen peroxide is 1 and also order for iodide is equal to 1. Then, we need to sum up the order. We get 2 for overall order. Thus, it is second order reaction. Next, let's go further in importance of hydrogen peroxide decomposition kinetics. The first one is industrial optimization. Industries commonly use hydrogen peroxide for bleaching, cleaning, sterilization, and wastewater treatment. Kinetics helps prevent premature decomposition, optimize temperature and catalyst conditions, reduce chemical waste, and control the release of oxygen. when the decomposition rate